Today we'll discuss about linear differential equations with constant coefficients, and we propose for the beginning an IVP problem, an initial values problem, and let us consider the equation y third by x minus y second equals to x, with the initial values y in 1 equals to 1, y prime in 1 equals to 0, and the second derivative in 1 equals to minus 1. So this is, as we can see, a linear differential equation of order 3. It appears the derivative of order 3, the higher order. So, in order to solve such an equation, we have two steps. In the first step, we have to solve the associated homogeneous equation, and then we have to find a particular solution of the non-homogeneous equation. If we denote this equation by E, we associate to this equation the homogeneous equation. Let's denote by H the homogeneous equation, which is y third minus y second equals to 0. In other words, instead of the free term x, we consider 0. And of course, we associate to this homogeneous equation the characteristic equation. So the characteristic equation of this homogeneous is given by r cubed minus r squared equals to 0. And this polynomial equation has 3 roots, and it is not difficult to see that from here we have r squared multiplied r minus 1 equals 0, which leads to the roots of the polynomial equation, the characteristic equation r1 equals r2 equals to 0, and r3 equals to 1. So, corresponding to these roots, having here 2 real roots, but the multiplicity of this root is 2, and another real root and symbol, corresponding to these roots, we have in the fundamental system of solutions for the homogeneous equation the following system of functions. So, corresponding to r1 equals r2 equals to 0, from the theory we have in the fundamental system e to the power of r1x, which is e to the power of 0x, and being a double solution, a double root, so this is x multiplied e to the power of 0x, and corresponding to r3 equals to 1, we have e to the power of 1x, so e to the power of x. In fact, here we have the fundamental system of solutions, which are 1, x, and e to the power of x. Of course, the general solution of the homogeneous equation can be written as the linear combination of the function from the fundamental system of solutions. And in this case, we can write here YH equals to C1 plus multiplied 1 plus C2 multiplied x plus C3 e to the power of x. So, in this case, we have the first part of solution, because according to the Picard-Lindelöf theorem of existence and uniqueness, the final solution of the non-homogeneous equation will be written as and I will write here, it will be written, the general solution is given by the general solution of the homogeneous equation plus a particular solution of the non-homogeneous equation. So, in the first step, we find the homogeneous solution, And then, in the second part, we have to find a particular solution of the non-homogeneous equation. In order to find the particular solution, we will use the undetermined coefficients method. I remind that in this case, we have to discuss about the particular solution according to the form of the free term in the non-homogeneous equation. And in this case, this is a very simple function, but generally we have the following frame. If the function f by x, which is the free term of the non-homogeneous equation, is of this form, e to the power of alpha x multiplied by p by x cosine of beta x plus q by x multiplied by sine of beta x, we have to identify who is alpha and who is beta corresponding to our function, which is x. And if the function f is given in this form, then we are looking for a particular solution of the equation, which is given by the following. Theoretically, it is x to the power of k e to the power of alpha x multiplied by another polynomial r by x cosine of beta x plus another polynomial s by x sine of beta x, where k is the multiplicity of the root r equals alpha plus I beta in the characteristic equation. So this is the multiplicity of this root, alpha plus I beta. Of course, with alpha and beta corresponding to our function f. We will see immediately in our case who is alpha and who is beta. And also about r by x and s by x, these are two polynomials having the degree maximum of the degrees of p and q. In other words, the degree of the polynomial r by x or s by x, both polynomials have the degree equals to the maximum of the degrees of polynomial p by x and the degree of q by x. Okay, so let's see in our case. In our case, for f by x equals to x, we have to see that we don't have in the function f by x equals to x. It follows that we don't have exponential. In other words, the coefficient of x in the power is 0. So alpha is 0. We don't have the exponential. Also, we don't have trigonometrical functions cosine and sine. It means that beta is 0. If beta is 0, cosine of beta x, cosine of 0 is 1, sine of 0 is 0. It remains only p by x, which is, in our case, exactly x. And q by x can be considered to be 0. So, we identify all the elements in f by x. According to these elements, we can say that yp by x must be of this form, x to the power of k. We are looking to the solution alpha plus I beta, which is in fact 0 plus I multiplies 0. This is 0. And the multiplicity of this root in the characteristic equation, as we can see, the multiplicity is 2. If the multiplicity is 2, we have to consider k to be 2. Yeah? So it will be x squared multiplied by e to the power of 0x is 1. R by x and s by x must be polynomials of degree 1. So a general polynomial of degree 1 is ax plus b. And of course, cosine of beta x, cosine of 0 is 1, sine of beta is 0. So this will be the particular solution. How to find the coefficients a and b? I said we use the undetermined coefficients method. In this case, we have to replace yp in the non-homogeneous equation, in E, in order to identify A and B. So, let's do it. We need, in order to replace in the non-homogeneous equation, we need the second derivative of y and the third derivative of y. Let's calculate the derivatives of y. So, yp prime equals to, as we can see here, in fact, this is ax cubed plus bx squared, and the derivative will be 3ax squared plus 2bx. And the second derivative of the function y second by x will be 6ax plus 2b. And finally, the third one, because we need the third derivative of the function to be replaced in the equation E, it is 6a. Okay, we have the third derivative and the second derivative we replace in the equation E. Replacing in the equation E, we have. So we have 6a, this is y third, minus y second, so it is minus 6ax plus 2b equals to x. So we replace now in x, and this is valid for any x real number. It must be satisfied for any x. So in this case we have minus 6ax plus 6a minus 2b equals x for any x real number. Of course, in this case, we have the equality of two polynomials of degree 1, and the equality holds for any x real number if and only if all the coefficients are 0. Consequently, we obtain from this equation, minus 6a must be the coefficient of x here is 1, and the free term of the first polynomial, 6a minus 2b, equals, the free term here is 0. So this is a very simple system, and we obtain immediately that a must be minus 1 over 6, and b, from here we can see that b is 3a. 3a multiplied here is minus 1 over 2. So we found the particular solution of the non-homogeneous equation. We can write it, and I will write here yp will be in this case minus 1 over 6 x cubed minus 1 over 2 x squared. So this is yh, this is yp. The sum of these two solutions will be the general solution of the non-homogeneous equation. We can write now the general solution of the non-homogeneous equation. According to the general solution, we have y by x will be yh, which is c1 plus c2x plus c3 e to the power of x plus, minus 1 over 6 x cubed minus 1 over 2 x squared. In order to determine the coefficients c1, c2, and c3, we will take into account the initial values of the problem. In other words, we have a unique solution for an IVP problem, and this unique solution is determined when c1, c2, and c3 are determined. So let's take into account the initial values. So the initial values are y by 1 equals 1, y prime by 1 equals to 0, and y second in 1 equals minus 1. This is equivalent to y1. In 1, for x equals 1, we obtain the equation c1 plus c2. I will write now the coefficients from the polynomial, which will be minus 1 over 2, minus 1 over 6, and plus c3 e to the power of 1, which is e, and this must be 1. The second equation, y prime. Of course, we need now y prime. Y prime of x will be, so it is c2 plus c3 e to the power of x minus, here is 3x squared, it remains 1 over 2 x squared, and here is 2x with 1 over 2 remains minus x only. And y prime in 1 will be c2 plus c3 e to the power of 1 minus 1 over 2 minus 1 equals to 0. And the third initial value is y second. So we need y second by x, which is, so according to this will be c3 e to the power of x. Here is x squared again is minus x and minus 1. If we calculate this second derivative in 1, we have c3 e to the power of 1 minus 1 minus 1 again equals to minus 1. So we obtain from the last equation, as we can see, c3e equals to 1, it follows that c3 is 1 over e. Having c3, we can calculate now c2. c3 multiplied e is 1 over e multiplied e. This is 1 minus 1 will be 0, so c2 in this case will be 1 over 2. So c2 is 1 over 2. Now, we are going in the first equation. And in the first equation we have c2 is 1 over 2 minus 1 over 2 disappear. c3 multiplied e, in this case c3 multiplied e is 1 again, with this 1 disappear. So what remains is only c1 equals, so this is 0 and these two terms are reduced, it remains c1 equals 1 over 6. Finally, we can write the unique solution of the non-homogeneous equation with the initial values which are given there. So the solution of the Cauchy problem will be y equals to, so it will be, I will write firstly the terms of degree 3 minus 1 over 6 x cubed minus 1 over 2 x squared, and now c2 is 1 over 2, we have plus 1 over 2x, c1 is 1 over 6, so plus 1 over 6, and don't forget to write c3 multiplied e to the power of x, but this is 1 over e multiplied e to the power of x. So to conclude and to put the solution in a nice form, we have y by x equals minus 1 over 6 multiplied by, it is x cubed, here minus 1 over 6 being a factor, we have plus 3 x squared. Now here we have minus 3x, and again minus 1, plus e to the power of x minus 1. So this is the final solution of our equation.